Okay, hi everyone. Good morning, all of you. Take every chance you get in life because some things only happen once. And today's best quote is be an example. Show kindness to unkind people. Forgive people who don't deserve it. Love unconditionally. Your actions always reflect who you are. Okay, so every one of these things is very difficult to follow actually. But they say you are really human. Because showing kindness to kind people, everybody will do it. But you try to show to the unkind people also. Forgive people who don't deserve it. Okay? Normally, who deserve also many people won't forgive. And love unconditionally. This is very important. Actually, that is the misunderstanding about the love. Right? And people feel loving is possessive. Okay? So that possessive nature, if it is there, then it's not love at all. There should not be any expectations. Then only we call it love. Okay, love itself is unconditional, but in our normal people's understanding is love is conditional. Like the more you feel jealous, or the more you feel possessed, people feel that they are loving more. But love is completely unconditional. Okay. So today is the birthday of Edmund Halley. I think everybody is very famous of Halley because Halley's comet, everybody knows about it. So he is English astronomer, geophysicist and mathematician who is best known for recognizing that a bright comet had appeared several times, calculating its orbit in 1682, and for successfully predicting its return. Halley became an influential fellow of the Royal Society. After originating the question that prodded Isaac Newton to write the seminal Philosophy Naturalis Principia Mathematica, this is the famous book of Newton, right? And Newton is a very shy fellow. He was hesitating to publish his work, and then Halley only has encouraged him, and he edited it and arranged its publication. Otherwise, nobody would have known about Newton. Halley was a professor of geometry at Oxford and later appointed astronomer royal. Halley identified the proper motion of stars, studied the moon's motion and tides, realized that nebulae were clouds of luminous gas among the stars, and that the aurora was a phenomenon connected with the Earth's magnetism. That is, this aurora borealis, which is seen in the poles. His prediction of the transit of Venus led to Captain James Cook's voyage to Tahiti. Okay, James Cook voyage. Okay, today we will have the lecture 32. And before going to that, we will see a little bit of division of 31. Okay, so we have discussed about FVM. And so general governing equation, we are written. Dou of rho phi by dou t plus del dot rho v phi is equal to del dot gamma del phi plus s. Okay, these things we have taken, and this is unsteady term, this is convection term, this is diffusion term, this is source term. Okay, so this is also called as divergence form. Okay. And in the last class we have considered 1D steady convection. So we have taken just del dot gamma del phi plus s phi. Okay, so whenever we consider FVM, integrate partial differential equation over the control volume. So we have seen the control volume to be something like this, and we have divided into number of cells, and the cell centers are called the nodes, and the node that we consider is P, and the left side node is called as west node, and the right side node is called as the east node. Okay, so I is P, I minus 1 is W, I plus 1 is U. Okay, like this we have considered, and we have to see that the boundaries coincide with the control phases, that is phases of the control volume. Okay, and we integrate it over the control volume like this. So dV will be there, and dV is nothing but k dx. Okay, so when you take 1D, we have taken 1D means d by dx of gamma d by dx k dx plus integral yes. S bar like this we will get, and this is to be integrated. So here dx is there, so it will be gamma a. Actually, when you differentiate, we differentiate from E phase to W phase for the control volume, because this is P and this is P and this is W. Okay, so gamma A d5 by dx E minus gamma A d5 by dx W minus S bar and delta V equal to 0. So it will be gamma E A d5 by dx and like this. Okay, the mainly thing is here d5 by dx at E, when you take it will be, it was here, will be there, and V will be there. So gamma A d5 by dx at E is phi E minus phi P by delta x E minus gamma W AW. d5 by dx at W is phi P minus phi W by delta x WP. That's got delta V equal to 0. Okay, so it will be something like this. Okay, this is the way we do it, and so here when you want so gamma E, okay, so here if I want this, it can be taken as average, because all values are known at the nodes. Okay, this can be taken as gamma P plus gamma E by 2. Okay, if it is yes,
sir, second equation integral over E to W or W to E?
WT WT. Thank you. Because it is from here to here. Okay, WT. That's why I write E minus W. Okay, thank you. Okay, this is the way we do. And so if I want the properties at a particular phase, so it depends on how it is varied. This is what is called here we take profile assumptions. So we can take stepwise profile, or you can take linear. Right? So each property can have its own profile, linear or stepwise. And the profile may vary from term to term. That is, for one term, maybe for convection term, you can take one profile. For diffusion term, you can take another profile based on your convenience. So in that way, we will have various schemes that will be developed. Okay, so anyhow, once you substitute, we write each equation like this: AP phi p is equal to uh, AW YW plus AE phi E plus okay, I will put B. And the S bar is written as SPTP, SP5P plus S, assuming a linear profile. Okay, this is the way we write it. So in general, it can be written as AP5P plus, is equal to sigma A and B phi and B plus B. Okay, this is the general form. So it can be explicit or implicit based on uh, phi and B. So if phi and B, that is neighboring points, phi and B are taken at n, it is explicit. If phi and B are taken at n plus 1, that is implicit. So phi p is always under n plus 1 only. So based on that, we can take it. And then we have discussed about 4 basic rules. So one is what is called as conservativeness. Means whatever enters a control volume should be same as whatever leaves the previous control volume. Okay, so this should be satisfied so that everything is conservative. And the second one is all coefficients are A's must have same sign. Okay, either positive or negative. So we take them to be positive. Okay, all A's must be positive. Okay, because any value of the neighbor, if it increases, the value at that point to be considered should increase. If that decrease, it should decrease. So they should have the same sign. And the next is the SP must be negative, because usually AP will be sigma A and B minus SP. Okay, it will come like this. And so if SP is positive, this may become negative for some, if SP is more than sigma A and B. So it should not occur like that. So if SP is negative, then this will be always positive. So this is the third one. And the fourth one, if there is no source, AP should be equal to sigma A. Okay. These are the 4 basic rules to be satisfied for any for the scheme to be stable. Okay. Okay, these are the things actually last class we have discussed. And today we take steady 1D convection diffusion problem. Okay, so again we take this derivative just del dot v5 del dot v5. Okay, so steady 1D convection diffusion. Okay, steady means this will be 0, and source term also I will neglect. So this and this will be there. And 1D means it will become d by dx of rho u5 is equal to d by dx of gamma d5 by dx. Okay, this is the governing equation to be considered. Okay, I have convection term and the diffusion term and 1D. Okay, and this is to be integrated. And we have to consider continuity equation also. Okay. And what is the continuity equation? Dou rho by dou t plus del dot rho phi equal to 0. And so steady, this is 0, and this is d by dx of rho u is equal to 0. So this is the continuity equation. And if I integrate, integral d by dx of rho u d. And again here w to e. So this will become rho ua of e minus rho ua of w equal to 0. If a equal to constant, then a goes off. It will become rho ue minus rho uw equal to 0. And here there is some, so for simplification, we will take rho u is equal to some f. So this will become fe minus fw equal to 0. So this is continuity.
Sir, we
Yes,
are doing for uniform flow, sir.
means
Sir, here we are doing for uniform flow.
uniform flow means
So we are taking area
it is a
function.
one-dimensional flow.
So area you are
Right?
taking
Okay,
function
it's
also.
okay. It's like uniform only. At a particular section, the velocity is constant. Okay, right.
Yes,
So
sir.
this is continuity equation, and if you take the momentum equation, like this. So this will become rho u a phi at is equal to gamma a basically like this. And so again, if a is taken to be constant, a can be cancelled like this. So here so d phi by dx at e is again phi e minus phi p and delta x p minus this is gamma e. Okay, this gamma w. Okay, like this we get. And again here also, because gamma is nothing but mu or alpha. This is diffusion coefficient. Okay, so usually we are taking them constant. So gamma e can be taken as gamma w. Okay. And we assume delta x also is constant. That is uniform grid. If for simplification I am taking, okay, it may not be uniform. Then delta xpe and delta xpw may be different if it is not uniform. And so here another parameter we define what is called as gamma by delta x. This is taken to be d, something like diffusion coefficient, and this is like the coefficient. Okay, yeah. And so it will become fe phi e minus fw phi w is equal to de phi e minus phi p minus dw phi p minus phi w. Okay, this is the way we get. Okay, the main problem here comes is, okay, phi e, phi p, phi w, they are nodes only. But here, phi e and phi w, small e and small w, these are the parameter at the faces. Okay, I don't have the values at the faces. I have values at the nodes. And how we substitute, based on that, we have various schemes. Okay, so we will see here. I write it again. F phi e minus Fw phi w is equal to du phi e minus phi p minus dw phi p minus phi w. Okay, so the problem comes when you take the phi e, phi small e, and phi small w. Okay, these capital letters, these are nodes, no problem. And de, dw, these are parameters. Okay, so here we take central difference. So central difference means phi e, and if I draw this, small w, small e, this is capital W, this. Okay, so phi e is taken to be phi e plus phi p by 2. Okay, that is central difference. Similarly, phi w is taken to be phi w is phi p by 2. So
Sir,
I
it's
can take,
average.
yeah. It is average. Okay, so I will show you. So this is the equation I am taking, and this is the continuity equation. And okay, this is this, and this is this. Fc minus F equal to 0. And this is the equation I am considering. Okay, now I have written. And now, if you take the central difference scheme, I take like this. Okay, so that is like, so here the difference I will tell you, if it is central difference like this. Okay, now suppose if I take upwind difference.
5A minus 4
So
5
what we mean by upwind is, suppose I want the value here. Okay, now I am taking as the average of these two, P and E, and if I take upwind, phi small e will be equal to phi P, and phi small w will be equal to phi capital W. That is, I am taking the value of the right side node. Okay, suppose
I
it
don't
is
understand, sir.
no, upwind means I take the, if I want to value at this phase. Instead of taking the average, I take the value at the node which is ahead of it. That is upwind. Is it clear?
Yes, sir.
So that is upwind. Okay, suppose the flow is in the reverse direction. Okay, so that is u is less than 0. Here u is greater than 0. U is less than 0 means flow is coming from this side. Then phi small e will be equal to phi capital E, because the flow is coming this side.
Sir,
And
it's
phi small w,
assumption.
no. If I know the flow is like this, I have to, if I take in this way, right, then I can take the values of the properties and the phases in whichever way I want, based on the physics, right? If it is actually diffusion dominating, I will tell you, right, later what happens, what problem we will get from this. Okay, so we have, if you remember the hyperbolic equation, right, their central difference FTCS is found to be unstable, and we have taken upwind differential to make the scheme to be stable. Do you remember that?
Yes, sir. Yes.
So we will see that actually under what conditions it happens and all. Okay, first for the time being, I am considering central difference scheme. Okay, central difference means the value at a phase is taken to be average of the values at the nodes on both sides. Is it okay?
Yes, sir.
Okay. So if I substitute them in this equation, so I will get Fe into phi E plus phi P by 2 minus Fw into phi W plus phi P by 2 is equal to dE into phi E minus phi P minus dW into phi P minus phi W. Like this I will get. Now I have to write in this form, AP phi P is equal to sigma A and B phi and B plus B. Okay. So in this form I want to write. So phi P I take common. If I take phi P common, what other things will be there? Uh, mm, I will get here Fe by 2, right? And here one phi P on the right side, dE is there, so plus dE. And dW also is there, minus dE, I think, plus only, plus dW. And here FW also is there, okay? And minus FW, like this. Okay, is equal to, if I want to take phi W, so what will be there? Phi W means dW is there, and plus FW and phi E. So dE is there, and phi E by 2 minus F. Am I right? So for 5p, here one 5p is there, here one 5p is there, here one 5p is there, and here one 5p. I am bringing all of them to this side. Okay, so this is AW. AW is equal to DW plus FW by 2. And this is AE. AE is equal to DE minus FE by 2. And AP should be, this is AP. AP should be AW plus AE minus SP. Okay. So what is AW? DW plus FW by 2. But here minus FW by 2 is there. So what I will do is I will write plus FW. And plus FW minus FW. Okay. So these two together is FW by 2. So DW plus FW by 2, this will become AW. Similarly, DE, here plus FE by 2 is there, but here minus FE by 2 is there. So again, I will add plus FE minus FE. So FE by 2 minus FE, if I take minus DFE minus FE by 2, it will become, so it will become AE. Okay, so now what are left is plus FE minus FW. Okay, so this is the way it will be. And then what is SP now? This is equal to minus SP, right? So SP is equal to FW minus FE. So then this will become minus SP, this like this. AW plus AE minus SP. Okay, so AW plus AE minus SP into 5P is equal to AW 5W plus AE 5E, like this, right? Where AW is DW plus FW by 2, AE is equal to DE minus FE by 2, and SP is equal to FW minus FE. Okay. So I am going to get in this form. Mistakes. Okay, like this. AW is in this table like this we will write. Okay, AP5P is equal to this, and AW is DW plus FW by 2, AE is DE minus FE by 2, AP is AW plus AE minus FE. So this is the way I have to write finally, so that when I write program, I have to know what are all the coefficients. Okay, so this is the way we'll do it. This is central differential scheme. Okay, now why should we go for other schemes? Okay, now we will see like this. And to be stable, we have to satisfy the 4 basic rules. Okay, and in that all A's must be positive. So here, this is the one I may have difficulty. Okay, so DE minus FE by 2 should be greater than 0. DW plus FW by 2, okay. Okay, but DE minus FE by 2 should be greater than 0. If this is to be greater than 0, DE minus FE by okay, DE is greater than FE by 2, or FE by 2 is less than DE, and FE by DE is less than 2. And what is FE by DE actually? FE is rho u, and D is gamma by delta x. That is rho u dx by gamma. Okay, this is you can understand that this is like Reynolds number. Okay, if gamma equal to mu, right? So Fu by dE is equal to Reynolds number. If gamma is equal to, if it is energy equation, gamma equal to alpha. Okay, so what this will become? Rho u dx by alpha. Do you know what is this? So this can be written as rho u dx by mu into mu by alpha. And this is Reynolds number. And mu by alpha is
Prandtl number.
Prandtl number. And Re into PR is
Reason
Peclet number, right? This is Peclet number.
Peclet number.
So Peclet number should be less than 2. If Peclet number is less than 2, then AE is greater than 0. But if Peclet number is less than greater than 2, right, then AE will be less than 0 and central difference will be unstable. Okay, so what do we mean by PE greater than 2? Means rho u or F. So F is far greater than D. And F is inertia force, which is rho u. And this is viscous. Okay, so that is viscous or diffusion. Okay, diffusive type. Okay, that is alpha by dx. Okay, so inertia force when it dominates, then central difference will not work. So what I mean by that is, if velocities are very large, okay, so the effect of diffusion is less. If it is diffusion only, then because the information moves all directions in the uniform way, central difference works. But if there is inertia force, okay, the velocities are large, then what happens? The influence I can see in the figure, okay, it is, if I have only diffusion, the information goes like this. Okay, so every value here depends on the figures, better figures I will show. This is what we call transport index. Okay, like this. If I have only diffusion, it will be like this, and P is influenced by W and E on both sides. Okay, but as my convection increases, so what happens is this will be gradually becomes like ellipse. And if my velocities are very large, and these will become that ellipse will be elongated, and I will get something like this. If Peclet number increases a lot, and this value at P depends on W but not E. Okay, so this is no convection, pure diffusion, and here diffusion is negligible, and if there is convection only, then it will become like this elongated ellipse. Am I clear about this?
Sir, please explain again.
Okay, if I have only diffusion, right, the information goes in this way, like a circle. And if my velocity increases, this instead of circle, it becomes like ellipse like this. Okay, and if I increase it further and further, so this will become something like this. Okay, this elongation will be in this side because it is going, the flow is in this direction. And here my P is there, here my P is there, here my W is there, my E is there. So, okay, so if my velocities are still larger, right? like this it will become something like this elongated ellipse-like thing. And the value here depends only on this side, but not on this E. Am I clear about that? Okay, just logic. Okay, forget about the figures and all. As I told many times, when the flow is in this direction, the value at this property depends only on the value behind it. It cannot be influenced by the flow after it. Am I right or not?
Yes, sir.
Okay, that is what is called as upwind differencing. So the central differencing will not work. Okay, if you always go in one direction from your room, who is there on the room behind you will not be known. Okay, something like that. Okay, so this is the way. If there is no convection, only diffusion, it will be like these circles. As the diffusion increases, the circles will become like elongated ellipses. And if convection is very large and diffusion is negligible, so the information goes like this. Okay, this small elongated ellipse. So as p tends to infinity. Okay, so here this is what I have shown. Fe by dE or Peclet number less than 2. If Peclet number is greater than 2, the yeast coefficient will be negative. That is Fe. So this violates one of the requirements of the boundedness and may lead to physically impossible solutions. And so we go for what is upwind differential scheme. Okay, so I have to have a logic. Okay, I don't know, the flow may be in this direction or flow may be in this direction when I am doing calculations. If there is a separation, at some point there will be right side flow and some point there will be left side flow. So I have to implement a particular logic there and it has to always work stable. Okay, so when the flow is in the positive direction, UW greater than 0, UE greater than 0. That is velocities at U, east phase and west phase both are greater than 0. Means FW greater than 0, FE greater than 0. Okay? And my equation is this now. Present equation is this. So here phi E and phi W I want to know. So phi small w is phi capital W. Here you can see phi small w is phi capital W because the positive direction the velocity is there. Similarly, phi small e should not be equal to phi capital E. It is phi e is equal to phi p. Okay, so this is the way I have to substitute here. Okay, so at phi e, phi p is substituted. At phi w is substituted. And this is the way if you write and again rearrange them. And this is the way you get the equation. Okay, so in the same way, if the flow is in the opposite direction, then phi small w is phi capital P and phi small e is phi capital E. So if UW, UE are less than 0 and FW and FE are less than 0, then I am going to get the equation in this form. Okay, but based on that, I have to have whichever way I want. So here it is written. When FW and FE are greater than 0, I am going to get DW plus FW here, DE here. And when they are negative, DW is here and DE minus FE is here. So if I want to write in a single way, so what I have to do is A capital W, that is here, should be equal to DW. DW is there, whether it is in this direction or in this direction. Yes.
So the first one is the flow is going towards east, and the second row is for the flow is going towards west. No?
What is that? I didn't understand.
So
See,
the
if
equation, two
UW
equations.
is less than 0, UE less than 0, the
Yes, sir.
flow is in this direction, and this is the equation I am going to get.
Yes, sir.
And
But sir,
yes,
how the two rows are coming for Fe and Fw? Like the two equations in the lower, sir.
so here this one you are asking,
No, sir.
this
Not
one,
sir. Niche below, sir.
this one.
Below side. No,
This
sir.
one?
This below side, sir.
This one.
Last one, sir.
This one. This one.
Yes, sir, yes.
So I have used this equation for negative flow and this equation for positive flow. Okay.
So, sir, how we are
So this,
combining both these?
that's what. Okay, I will tell you. Okay. So this is AP, this is AW, and this is AE. When the positive is in the positive direction, that is written in the first row. Okay.
Yes, sir.
And for the second row, when they are negative, I'm going to get this as AP, and this is AW, and this is AE. That is written here.
Yes, sir.
Okay. And now, instead of having two rows, I want to have a single row.
Sir, but flow can be only taken place in the one direction or at a time, sir?
That's what at some points it may be positive direction, at some points it may be negative direction. When there is a circulation taking place, okay, some points there will be positive direction. At some nodes it will be in negative direction. Am I right or not?
Yes, sir.
So when I consider that particular node, I have to take the equation according to the direction of flow.
Okay, sir.
Okay, I have to keep it in if loop. If u is greater than 0, okay, so then AW is this, AE is this. If u is less than 0, then like that I have to write it. Is it clear? So instead of writing that way, I can have this particular form. So here if you see AW, these two I have to write as a single term. So it is written dW is there common. So I am writing dW plus max of FW 0. So when FW is greater than 0, it should be there. And when FW is less than 0, it should not be there. Am I clear? So when FW is less than 0, I should not add anything. It should be 0. But when FW is greater than 0, I have to add FW. So here I am writing maximum of FW 0. If FW is positive, right, I have to add it. If the FW is negative, I should not add it. Am I clear about this? You see these two. If FW is positive, I have to add FW. If FW is negative, I should not add anything. So here I am writing, you have to add maximum of FW 0. If FW is positive, I will add this. If FW is negative, I will not, 0 is taken here. So I don't add anything. Am I clear about this?
Yes, sir.
Yes, sir.
Similarly, AE if you take, DE is there common, and FE should be added when FE is less than 0. Okay, so if FE is greater than 0, I should not add anything. So max of 0 and minus FE. So minus FE is to be added when FE is less than 0. When FE is greater than 0, I should not add anything. So I'm writing max of 0 minus FE. Okay, so this way if I write in the program, I need not write if condition. Okay, both are right. I can use either this or this. Both are right. So if I write this in the logic of the program, I have to write if condition, and I have to write like that. Okay, but here, if I write in this way straight away, no problem. AW is equal to DW plus max is a function available in the MATLAB or C or anything. So max of FW0, if I put like this, it will work. Am I clear?
Sir,
Yes.
sir, I cannot understand, sir. Why phi W equal to phi P?
Why?
Phi W equal to phi P.
This
Phi
one
P.
here.
Yes, sir.
Okay, this, if flow is in the negative direction, I have P here, small w, small e, here capital E, capital W. Okay, now flow is taking in this direction. Okay, I want the value at this point. So which value I should take, at P or capital W?
Sir, P, but sir, here del phi del x at W equal to phi W minus phi V by its distance. So phi W will be phi P something its calculation.
No, no, no.
So it's
See,
backward difference. I just like,
no, it's not backward difference or anything.
sir, why we take
I want the values at the faces.
yes sir.
Small e, small w are the faces of the control volume.
Okay. So it's
Okay,
assumption, sir.
I have the values at the nodes only. At the P, at the capital W, at the capital E, I have values.
Yes sir. Yes.
And now I want the values at small e and small w at the faces. So which value I have to take there? I don't have value there.
Yes sir. Sir, that means it's a logical assumption.
Yeah, logical assumption, you can make any assumption, but it should satisfy the physics. Okay, so if my in the equation the flow velocities are small and the diffusion or the alpha or mu is large, then the information moves in uniformly in all directions. So the value at this point are to be taken as the average of w and p. That is
Yes
central
sir.
difference.
Yes sir.
But if I have a dominant velocity in one direction, so if the information is moving in this direction, the value at the face, small w, can be p only. It will be independent of capital W.
Yes. Yes.
That's what we have written here.
Yes sir.
Okay. Okay. This is what is called as upwind differencing. If you write in this way, so there will not be difficulty for the stability. So all will be positive. Okay. So this will be positive and this will be positive. Because Fe is negative. Okay. So negative of negative will be positive. And so this AE will be positive. And there is what is called as hybrid differencing. I will
Sir,
not
in the
go in
previous
detail.
slide, sir, can you go
Yeah.
for it? Sir,
Yeah.
UW is greater than 0 and UE is greater than 0. Then you've written F in bracket FW is greater than 0 and FE is greater than what
Yeah. Yeah. Both
means?
are greater than. When they are greater than 0, right, I have to take this way. Because flow is in this direction, right? So here this value will be taken to be capital W. And here the value will be taken as P.
Yes, sir, but sir, both the conditions should satisfy for U and FW, sir.
Didn't
So
understand.
the flow which is taking place from left to right, we are we are uh, we know from U is greater than 0 and U is greater than E is greater than 0, no sir.
Yeah.
So but
If
for
see, if
FW,
flow is in this positive direction, positive x direction, both the UG and UW are positive.
yes sir.
That is, flow is in this direction.
Sir, I am asking that
Yeah.
U and F both should be greater than 0 to flow
Yeah.
to.
Because F is equal to rho U.
Okay, sir. Okay, understood.
Okay. So when both are positive, these also will be positive.
Yes,
And
sir.
here, yeah, like that. So there is a hybrid scheme where I have to use central difference and also the upwind differencing based on the value of PE. Okay, if PE is less than 2, okay, that is minus 2 plus 2, then I can take central difference scheme. If P is greater than 2, I have to take upwind differencing. Okay, so if you put this particular logic, okay, I am not going to explain, you can just think about it. So this will work. And this will take, according to the value of velocity, it will take central difference or upwind differencing or downwind differencing, whatever you say. So based on the value of the PE. Okay, so this is the way I can have what is called as hybrid differencing scheme. And there are various other schemes. Okay, we will not go into the details, but just I will give you the formula. there is what is called as, okay, this is for multi-dimensions. Okay, so AW, AE, AS, AN, AB, AT, all of them can be written in this way. And we have what is called as power law scheme. And power law scheme, AW and AE will be like this. Actually, this comes very near to the analytical value, but there will be calculations, power 5 and all. So normally is not much used. Okay? This is power law scheme. There is another important scheme I will come to, what is called as quick scheme.
Can you explain again the power law?
It is just okay, this is this. Okay, you need not worry much about it. Okay, so this value is 1 minus 0.1 Factored number to the power of 5. Okay, so just it is a literary interest, you learn it, it's not necessary. Okay, so there is another scheme you understand, there is a power law scheme. Okay, so this satisfies that. Okay, so there is another scheme called as quadratic upwind interpolation for convection kinetic. This is what is called as quadratic upwind interpolation convection kinetic. So this is what is called as fixed scheme. It is just nothing. It is like second order upwind scheme. It is second order upwind scheme. This, if you remember, we have read when we studied as FTBS, FTBCS like this. Okay. So when we studied FTBCS, forward time, backward and central space. Okay, backward for convection and central difference for diffusion like this. So when we taken backward means this is upwind. So this can be first order or second order or third order, like that we have seen. So if I take first order, I will have what is called as diffusion error. But this is stable. But when we have taken second order scheme, we will have dispersion error and we have to use damping. And then third order is better, but more time it will take for calculation. Okay, so here it is a second order upwind scheme. If you take, that is what is called as fixed scheme. Okay, what I have to do is upwind, suppose if P, W, E, and one more point you will take in east, and here west. And the faces are small w, small e. Okay, so here the upwind means, so for P, the value at E, we are taking at P or E based on the velocity. But if I consider 2 points on this side, then it is second order accuracy. Okay, so this is like this.
So last one, there was internet issue, so please repeat.
Okay. So here, if I take 2 points before this, okay, I have P, I have capital W and WW. Here, this is the face W. And suppose the velocity in this direction. What we are taking is 5 small w is equal to 5 capital W. This is first order. And if I want to take this WW also into consideration, okay, so second order upwind it will be.
Okay, sir.
Okay. So here the general second order thing is phi on the face is equal to 6 by 8 phi I minus 1 plus 3 by 8 phi I minus 1 by 8 phi I minus 2. Okay. So if phi small w, if I want 6 by 8, okay, So here if I want, I have to use 6 by 8 phi I minus 1 is phi W. And 3 by 8 phi I means phi P. And 1 by 8 phi I minus 2 means phi WW. Like this I have to write. Similarly, for the right face E, small e, I have to consider capital P, capital E, and EE I have to consider. Okay, so this is the way I get. Okay, then just you understand the substitution of this. Once you substitute, again you have to rewrite them in the way I want, like AP 5P, AW 5W, like this. And these are the coefficients. And again, this is for u greater than 0. And if it is u less than 0, then you have to consider accordingly, right? So you have to consider the point on the direction side, okay? 2 points on this side. If it is going this way, 2 points on this side I have to take. If I going this way, 2 points on the right side I have to take. So based on that, your coefficients will change. This is what is called as quick scheme. Okay, you understand? There is a scheme, quick scheme, which takes second order upwind scheme. Okay. So this is the way you get. Okay, this is this. You understand the logic? What is the way? It is very simple. Only thing is, here we have different schemes because there is convection and diffusion. If there is only diffusion, central difference is the best. Okay, whatever we have used it for parabolic equation. But when I have convection dominant, which is like hyperbolic equation, if you remember, I am just recollecting, revising of whatever we have done in the finite difference methods. If you remember, in hyperbolic equation, we have seen that FTCS method fails. And we have taken upwind differencing, which is stable. Why it is? Because I have explained here. There is diffusion and convection is there. If diffusion is dominant, central difference will work. If convection is dominant, then I have to go for upwind differencing. So based on the type, if I take anything, we have a hybrid scheme. And if you are sure that the flow is taking only in one direction, then I can have, again, second order upwinding I can take. Again, there also, based on the velocity direction, I can take 2 points on the flow direction to have the value at the face. Okay, so that is the way. If you do, we have what is called as quadratic upwind interpolation for convection kinetic scheme, quick scheme. Any questions? So this is the 5th chapter in both Patankar and also Versteeg. Okay, you can just go through them. Okay, then if there are no questions, we will go for the story. So when the wind blows story. Okay, so what is this? Once there lived a farmer who owned a land along the coast of the Atlantic Ocean. Even after letting out several advertisements for recruitment to take care of his farm, no one seemed to sign up for it. Okay, he has advertised for a post, but nobody is applying. And after months of advertising and request refusals, a man approached the farmer for the job to take care of the farm. And then in the interview, he asked, "Do you have any skills or experience to work on a farm like this?" The farmer asked him. "Well, I may not have enough experience, but I can sleep when the wind blows," replied the man. This fellow is surprised. Actually, he has to be more proactive and more active. When the wind blows, he has to take care of all the things. But he says, "I can sleep when the wind blows." Okay, he didn't like that answer, but although the farmer wasn't much convinced by the man's answer, the farmer was too desperate to have someone to help him on the field that he hired him anyway. And he has taken that fellow and hired, and he started working, and the man worked well around the farm. The farmer was pretty satisfied with the man. Okay, now there comes, then one stormy night, the wind howled, waking the farmer. Okay, suddenly got up, there is a lot of wind is there. The farmer is in tension. He went immediately, the farmer immediately got off his bed, grabbed the lantern, and headed towards the quarter where his helper was sleeping. "Wake up," the farmer yelled, throwing the soundy sleep of man off the bed. A storm is coming. Tie things down before they get blown away. And the man sat up and said, "No, sir, I told you I can sleep when the wind blows." The farmer turned red with fury after listening to this. He controlled all his will to fire the man because at that moment it was more important to secure his fields and barn than to argue with the helper. The farmer ran out to tie the things up and was surprised by what he saw. All of the haystacks were covered with tarpaulins. The chickens were in the coops. The cows were in the barn. The doors were closed and barred, and the shutters were firmly secured. Everything was tied down so that nothing could be blown away. So this is what actually says. He tells, I will take care of everything and I can comfortably sleep even the wind blows. Okay, that's what he meant. The farmer smiled as he comprehended it. Now he understood what his employee said. Now he understood what the man meant by when he said he could sleep when the wind blows. He went off to bed and slept soundly through the storm. Okay, what is the moral? When you are prepared physically, mentally, and spiritually, you have nothing to fear. Can you sleep when the wind blows through your life? Okay, so we have to become. So sometimes many parents, what they do is they spend everything for the children, and they apply for loans also for the children to give them a beautiful life. And finally, many times what happens is the children will go away without taking care of the parents. Now all these old age homes are flooded with the people. It is completely full only because of such type of people. So if they take care, okay, they have to take care of the children, but not at the cost of their future. Okay, they have to think about their future also and children's future. But if you think about only children's future, later your future will be horrible. So that's what actually you have to be prepared physically, mentally, spiritually. Then you have nothing to fear. You can sleep when the wind blows through your life. Whatever problem comes, because you are confident that you can look after yourself. Okay? So that's it. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.